Thank you, Joe, for this very nice introduction. So, welcome everyone. I'm super excited that we are currently 124 people, way more than I expected. So our first speaker for these lectures is Luca Sciarini, who works in Geneva currently, in actually the same office. So Luca did his physics bachelor at the École Polytechnique Fédérale de Lausanne, and then he did an Erasmus at the University of Uppsala in Sweden. He did a master in astrophysics at the University of Geneva, and it was under the supervision of Professor George Maine and Dr. Sylvia Ekström. And the thesis was focused on the explosive nucleosynthesis of solar metallicity and first-generation stars. So nowadays he's doing his PhD under the supervision of Sylvia and as a co-supervisor Patrick Eggenberger. And his thesis focused on the evolution of binary and triple system through numerical simulations with an emphasis on the importance of the stellar physics ingredient, in particular the transport and mixing mechanism on the evolution of multiple systems. So his defense is planned for December 2026, so stay tuned for the next 2 years. And if you are more interested in his work, it has currently published one paper in ANA in 2024, and it's entitled Dynamical Tides and Binaries, Inconsistencies in the Implementation of Zan's Prescription. A very interesting paper that I recommend you to read. Anyway, now I would like to give Luca the floor to start his presentation, and I will ask all the participants now very kindly to mute yourself such that we can fully enjoy Luca's presentation. So please, Luca, the sharing is working, so you can start presenting.
Thank you, Sophie, for the introduction. I will just, it's not frozen. So thank you also for giving me the opportunity to present this talk. It's the first seminar series, the first seminar of this series on massive stars, and it will be focused on observational phenomenology. More precisely, the question that I will want to tackle is the following: what are the key observational constraints that stellar models need to reproduce? And here is the outline of the presentation. We'll start with a generic introduction about massive stars and give a bit of nomenclature. Then the main part of the presentation will be focused on the overall locations of stars in the HR diagram. We'll discuss different problems related to that. Then I will move on to rotational velocities and chemical enrichment, and finally discuss end products of massive star evolution, supernovae, black holes, gravitational waves, gamma ray burst. I will then summarize my results and mention additional source of constraints that I don't have time to talk about in this presentation. So massive stars, as you all know, play a very important role in the universe. They are contributor to chemical enrichment. They control the star formation, and because of this, they are the main drivers of galactic evolution. Massive stars are rare, and because of that, statistics are often pretty limited. And also, important observables of massive stars are sometimes difficult to infer. On the other hand, stellar models are very important tools to understand the physics of massive stars, but they suffer from simplifications, uncertain free parameters, and compromises between efficiency and accuracy. So the main line of this presentation is the following one. What are the key observational constraints stellar models need to produce, and how can these constraints help refining the models? And so to start with a bit of nomenclature, I provided here a little glossary of massive stars, different objects that I will mention during the presentation. So I just give here the list. These are observational definitions, and then I will also try to tackle a bit how, in terms of stellar evolution, these different objects can be connected to each other. So we have O and B stars, which are hot and massive stars with temperatures range given here. Supergiants, which are very luminous stars with different temperature ranges. Luminous blue variable stars, which are hot and extremely luminous stars that are which main characteristic is that they undergo episodic outbursts and variations in their brightness. And finally, Wolf-Rayet stars are very hot stars, which spectrum is dominated by broad emission lines of different elements, in particular helium, nitrogen, carbon, and oxygen, with very little traces or no traces at all of hydrogen. And just to show you a bit how these different populations of stars can be seen in an HR diagram. So here we have an HR diagram from Ramachandran 19 of massive stars in the SMC wing. And we can recognize here OB stars, blue and yellow, red supergiants here. There is one example of an LBV star. And also Wolf-Rayet that are very bright and also much more compact stars. Okay, so the first important part of this presentation focuses on the location of stars in the HR diagram. And the question that we want to tackle is the following one. Can stellar models reproduce the observed distributions of massive stars in the color magnitude or HR diagram? And as an example, you can see here the color magnitude diagram of supergiants in the Andromeda galaxy obtained from photometry by Drought 2009. And the first thing that I want to discuss is the connection between different stars, different categories of stars that I mentioned before, and it's known as the Conti scenario. It was initially suggested by Conti in the 70s, and it's made on mainly it's based on mainly two observational aspects. The first one is that O stars, blue supergiants, and LBV stars typically have important mass loss rates. And the second one is that Wolf-Rayet stars typically have peculiar spectra with strong and broad emission lines of helium, nitrogen, carbon, oxygen, but without really traces of hydrogen. And so the Conti scenario is the idea that at the beginning of the evolution of stars, of massive stars, winds will be maybe sometimes important enough to remove the whole hydrogen envelope. And in this case, it will create a star which doesn't show any hydrogen anymore. And this would be the formation channel of Wolf-Rayet stars. A star which has just lost its hydrogen envelope would be a WN Wolf-Rayet star. And if on top of that, the helium layers have been removed as well, in this case, you get a WCWO type Wolf-Rayet. And the general evolutionary channel is summarized here. You start from a no star that becomes a blue supergiant, an LBV, and at the end of this evolution, a Wolf-Rayet star. And just to schematically show that, I tried to illustrate this with a simplified abundance profile of a massive star, pretty evolved one actually. And so the idea is that for people who are not really familiar with stellar evolution and the way we present things, this corresponds to the interior of a massive star. We are using the mass coordinate, the Lagrangian coordinate, starting from the center to the surface. So something that is to the left would be at the center of the star, and at the right would be at the surface of the star. So this is what we can observe. And what are shown here are the mass fractions, so the abundance of different elements. I only included here hydrogen, helium, and the CNO elements. And so if we would assume that if the star is subject to important stellar winds during its evolution, what can happen is that at some point, the whole hydrogen envelope, so the whole layers, external layers where hydrogen was present, are removed. And we can see that if the winds are important enough, at some point we reach a state where we can't see all of the layers that were containing hydrogen have been removed. This would correspond to the new surface of the star. And since no hydrogen is present in the surface anymore, well, they can't be seen in the spectral lines. And so what we have now on the right part, would be typically the abundance profile of a type WN Wolf-Rayet star that still has some nitrogen and helium layer. And if the mass loss was even more important, it could even at some point remove the layer where helium and nitrogen were present. And in this case, this is now the surface of the star. We can see that only carbon and oxygen are present. So in this case, we have a WCWO star. And in terms of calculations, this can be nicely represented by these calculations by Gros in 2014. They performed a detailed calculation of a 60 solar mass model using the Geneva code, and also computed the output spectrum at different phases using the code CMFGEM. So what you can see on the left are the evolution of the star in the HR diagram. With on the upper panel, the color corresponds to different evolutionary stage. So it corresponds on the abundance of the elements in the core of the star. On the other hand, on the lower part, the color referred to different spectroscopic phases. So how the star looks like in the sky. And on the right, you can see the evolution as a function of age of the mass fraction in the surface here and in the center of the different elements in the star. And so what you can see is that at the beginning of the evolution, the star still has some hydrogen and helium at the surface, and it appears as an O star. At some point, it reaches the LBV state, where winds will be typically very important, until the moment where hydrogen is completely removed at the surface. And when this happens, it's exactly the moment where the spectroscopic phase becomes the WN. So the star appears as a WN star. And a bit further, we see that even nitrogen is depleted, and it's exactly the moment where the star becomes a WC Wolf-Rayet. So now the next point that I want to talk about is the main sequence width. On the observation part, the main sequence width corresponds to the extent in the region of the HR diagram where stars spans their main sequence. It's one of the most important features that stellar code needs to reproduce because it's the longest phase of evolution of massive stars, so that's where most stars are observed. There are different studies showing, in particular the one of Castro 2014, that show a discrepancy between the observed main sequence width and that of certain models. And what does that mean exactly? It's well represented in this plot by Castro 2014. It's actually a spectroscopic HR diagram, so it's a bit different. Instead of the luminosity, they're using a proxy for the luminosity, which is obtained in this way. So it's the effective temperature to the 4 divided by the surface gravity. And so what they're showing in this diagram are observed stars represented by density contours, where dark regions in the parameter space corresponds to regions where a lot of stars are observed, whereas white regions are regions where no stars are observed. And on top of that, they are showing evolutionary models. On the left, the Geneva models, and on the right, the bone models. And if you look closely, there is one region. We can clearly see that the density of the observed star drops suddenly at some region, and they interpret this as the terminal age main sequence line, essentially. So everything between this line, that is the 0 age main sequence, and this line, which the terminal is age main sequence, is considered to be the observed main sequence width. And what you can see is that on the other hand, the model's main sequence width, which is the one obtained from simulations, are not exactly matching this observed main sequence width. In general, the model's main sequence width is a bit in this case smaller than the observed main sequence width. And so the thing is that on the theoretical part, the model main sequence width is actually very sensitive to different input physics that are used, in particular the overshoot. I won't enter too much into the details because there will be a dedicated presentation about convection, but let me just mention that convective overshoot refers to the phenomenon where convective motion extends beyond the region where it's expected to occur according to the standard stability criterions. There are mostly two, the Schwarzschild and the Ledoux criterions, that are telling you if the layer will be stable or unstable, i.e. convective. And actually, they're obtained on a force acceleration consideration, comparing two gradients, the radiative and the adiabatic gradient. And when the radiative gradient is bigger than the adiabatic gradient, then the layer is convective. On the other hand, when the radiative gradient is bigger than when the radiative gradient is smaller than the adiabatic gradient, it's a radiative layer. And the thing is that there can be some region in the middle where the two gradients are almost equal. And in this case, what the criterion will tell you is that any bubble coming from the convective region will not be accelerated, but it could still keep its inertia if it has some. So if we imagine that we have some bubble of matter coming from the convective region that were accelerated in this region, reaching this non-accelerated region, they could still expand and overshoot in this overshooting region. And the length of this overshooting region is actually not very simple to obtain based on these simple criterions. What you would really need to obtain the length of this region would be a proper modeling hydrodynamical simulation to really know the size of this region. So what is typically done in stellar codes is that the length of this overshooting region is parameterized with a free parameter alpha overshoot. And this parameter is actually pretty uncertain. And so people have shown that the thing is that this alpha overshoot controls the size of the convective core because depending on this value, you increase essentially the size of your core. And because of that, you also increase your main sequence lifetime. And so it's in this case pretty easy to understand that increasing the value of alpha overshoot will increase the main sequence width of your model. And so actually what can be done, and it's kind of the reverse engineering process, is that if you observe if you do some observations and you obtain some observed main sequence width, you can then tune the value of your parameter alpha overshoot to reproduce the observed main sequence width, and it's the idea of the calibration of alpha overshoots. Okay, let me now move on to the blue to red supergiant ratios. It's one of the oldest problems of massive star evolution theory. It's the ratio of blue to red supergiants. So it's simply defined in this way. The B over R ratio is the number of blue supergiants divided by the number of red supergiants. The thing is that this ratio has been shown to increase with the metallicity, as we can see in this figure by Egenberger. Using different supergiants in the Milky Way and the small Magellanic Cloud. And the problem is that if you move to the theoretical part, single star models show the opposite trend. The ratio increases with the metallicity. So at high metallicity, you're expecting to see more blue supergiants. But if you try to make stellar models, you actually obtain an opposite trend. Here I compared Geneva tracks at different metallicities that have exactly the same input physics apart from the initial metallicity. These are solar metallicity models, and these are very low metallicity models from Sciarini 2024. And so if you look at the evolution in the HR diagram, what you can notice is that at solar metallicity, you obtain more red supergiants than at low metallicity. And it's kind of the opposite trend of what we have from observations, where at high metallicity, you would expect to see more blue supergiants and more red supergiant at a low metallicity. So the explanation for the metallicity trend is actually still pretty unclear. But there are still some clues that we can mention. Firstly, the models that I just showed were non-rotating models. And it's actually, you can actually show that accounting for rotational mixing, especially among low metallicity models, changes a lot the path on the HR diagram. Here I'm just also again using the models of Sciarini at low metallicities. The only difference are that here the models are rotating and have then some rotational mixing. And as you can see, by accounting for rotational mixing, stars transition more to the red, so you have more red supergiants. And at higher metallicities, on the other hand, if you remember what we said before, strong stellar winds can sometimes remove the envelope of the stars. And this actually typically make them go back to the blue. And so they spend less time as red supergiant or completely avoid the red supergiant phase. So this is kind of going in the right direction because, as you know, stellar winds increase with the metallicity. So at higher metallicity, you have more winds. And so it increases this process that star will spend less time as red supergiants. And finally, let me also mention that there are some studies showing that blue supergiants can also just simply result from binary interactions, and this complicates the picture. Okay, let me now move on to blue stragglers. So what are blue stragglers? Blue stragglers are stars found in a star cluster that typically appear bluer and also more luminous, i.e. younger than any other stars in the cluster. Because stars in cluster are typically expected to be approximately of the same age. And because of that, we often use isochrones. They're useful tool to identify outliers. And here I give you the definition of an isochrone. It's a curve on the HR diagram or the color magnitude diagram that represents the evolutionary stage of stars that all have the same age but different initial masses. So let's have a look at that in plots. Here are the CMD of two different clusters. And you have a population of star in this cluster. And the lines here are theoretical isochrones. And you can see that depending on the value of the age that you fix for your isochrone, you have different lines essentially. And what has been shown for these clusters are that even when you take the best fit to your population, so the best age for your isochrone, you will still have some outliers. And you can see them here and here. They essentially are much more luminous and blue than the other stars in the cluster. So they seem to be younger, even though we expect all of the stars of the cluster to be born pretty much at the same time. Blue stragglers are actually pretty difficult to explain with single star evolution. And all of the potential explanations typically involve multiple bodies interactions, binary or triple systems evolution, mergers, rejuvenation by mass transfer, or dynamical interactions in triple systems. Okay, another point related to the position of stars in the HR diagram is the paucity of star near the zero age main sequence. It has been reported in several studies, including recent ones by Holgado and Schutemeyer. Here is the Espon-Russell diagram of luminous star in the SMC from Schutemeyer. So all of the red dots are observed stars, and they also include tracks, stellar version tracks. And what you can see in this diagram is that I've added the dark line here corresponding to the zero age main sequence line. What they have in this plot is a line that they draw at half the age of the main sequence. And so since this is half the age of the main sequence, we would expect to observe the same number of stars in between these two lines, so left to this half main sequence age line, than to the right. But what we see is actually very different. As you can see, there are few stars left to this gray line, so you have few stars near the zero age main sequence. And there are different possible explanations for that. What they say in the paper by Schutemeyer is that young massive stars are often probably still embedded in their birth cloud. And because of that, maybe they're more difficult to observe. So it will be just more an observational aspect. We don't see them because they are hidden by a cloud. And what Holgado proposed is that actually young massive main sequence massive stars are still accreting mass. And this changes the theoretical birth line for stars in this population. So I'm trying, this is what I will try to explain in this plot. What you can see here is in the gray line is the usual zero age main sequence line. And essentially what are these assumptions for this line is that in principle, models will directly start with a structure that is at hydrostatic equilibrium and start to burn hydrogen from that. And then stars will evolve away from this zero-age main sequence line. But if you think in a more in a stellar formation point of view, there is not really any reason that a star would just appear directly with all of this mass and then start suddenly to fuse hydrogen. A more realistic picture is that there is some accretion happening. The star slowly grows in mass until it reaches a moment where it's massive enough for igniting hydrogen, but it could still be accreting mass while burning hydrogen. And so that's essentially what Holgado have been simulating. They accounted for mass accretion after the beginning of the main sequence, starting with the pretty low mass seeds. They started with a mass of 8 solar mass only. And if you combine the effect of the main sequence evolution that drives you away from the zero-age main sequence line, and the mass accretion that kind of make you evolve parallel to this zero-age main sequence line, you can kind of explain, you can obtain a different theoretical birth line that is given by this green curve here. And so it's maybe a bit more realistic theoretical birth line, assuming that the star was already burning hydrogen when it was still accreting mass. And so you can see that assuming this constant accretion of 10 to the minus 5 solar mass per year, it's the green line, they obtain a birth line that is much more consistent with the observation. Okay, the last thing I want to talk about that is related to the position of star in the Schar diagram is the mass discrepancy. It's another pretty old discrepancy between stellar models and observations. It was firstly identified in the early 90s by Groenewegen and Herrero. It's a positive discrepancy between the evolutionary mass and the spectroscopic mass. So I've given here some schematic definition of these two quantities. There are essentially two different ways of obtaining a value for the mass, but in the end, they both want to measure the same quantity, which is the mass of the star. The spectroscopic mass is directly obtained from observed quantities. So if you have at the same time the surface gravity, the luminosity, and the temperature, you can directly obtain a value for the mass, and that's the spectroscopic mass. The evolutionary mass, on the other hand, is obtained fitting some observed quantities. For example, if you only have the luminosity and the effective temperature, and use theoretical stellar track, you can then obtain a value for the mass. So it's represented here schematically. If you have, for example, two stellar tracks for different eventual masses and some observational point in the middle, you can make some sort of interpolation and you obtain a value for the mass. And this is essentially how you get a value for the mass. I will just mention that this is kind of the simplest way to do that, and there are some more modern ways that involve a bit more observable quantities, such as what is done with the bonsai code. And essentially, these two masses should be the same because we are measuring the same quantity. But what has been reported in many studies, including recent ones, is that there is actually a discrepancy between these two masses. Usually, the evolutionary mass is bigger than the spectroscopic mass. And there are other recent studies that don't find evidence for this discrepancy, and I will show results of the two sites. So here on the left, you have the mass discrepancy as it was described originally by Herrero. And as you can see, there is this 1-to-1 line here where you would expect theoretically to see all of your masses. But you see that in general, the evolutionary mass is bigger than the spectroscopic mass. Here is a more recent paper by Mahi, 2015. And again, we can also see some evidence for positive discrepancy between evolutionary mass and spectroscopic mass. So on the other hand, we can see here a plot by Ramirez Agudelo, 2017, where they don't really obtain a systematic mass discrepancy. They have a large scatter in their data. Sometimes the evolutionary mass is much bigger. Sometimes it's actually the spectroscopic mass. So in this case, they can't really claim that they obtain a systematic mass discrepancy. So there are some people considering that the mass discrepancy is still an issue. Others rather consider that it's more a consequence of the large uncertainties that are associated to each type of the mass measurement. And there is a nice discussion in the paper by Markova 18, where they discuss the discrepancy in evolutionary masses obtained with different sets of stellar tracks. So they essentially obtain two different values for the evolutionary mass using different sets of stellar models, because you need a stellar track to obtain a value for the evolutionary mass. It's what they show here. They show the ratio of the evolutionary mass obtained with the Bonn models with the one obtained with the Geneva models as a function of mass. So we would expect normally to obtain only one in this case, if the two stellar tracks would provide corresponding masses. But what we do see is that depending on the mass and depending on the objects that we are considering, there is also a mass discrepancy actually between the two different evolutionary masses. And so they interpret that as by the fact that there are different input physics in the two sets of codes. Overshoot, as we discussed before, it can definitely alter the evolution in the HR diagram. But there are also different treatment of the angular momentum transport, rotational mixing that can all cause some differences in the evolution in the stellar tracks. And so maybe the fact that two different sets of codes give very different value for the evolutionary mass is a sign that it's maybe a too simplistic way of obtaining a value for the mass. And so what they show here, again, are the ratio between the evolutionary mass and the spectroscopic mass obtained with the two different sets of codes as a function of the mass. And they show that depending on the code they're using and depending on the mass range, they can obtain sometimes a positive discrepancy, but there are they can also obtain sometimes some negative discrepancy. All right, let me now move on to the second part of the talk that is focused on rotational velocities and chemical enrichment. So on the observational point of view, O and B stars can show different nitrogen enrichment and sometimes also important rotational velocities. This is usually represented in the Hunter diagram, that is comparing V sine I to the N/H ratio. As you can see here, that's the Hunter diagram from here, the 2008 paper for 135 B stars. And you can see that we have a lot of different distribution in this diagram. Stars that are rotating fast, stars that are largely nitrogen enhanced, some stars that are a bit in the middle. And so on the theoretical part, how can we actually explain these distributions? Well, on the theoretical part, stellar models that account for rotational mixing can produce some important surface enrichment. And I will try to explain how this works. I think that everybody is familiar with the Sciano cycle, that is the way to burn hydrogen in the center. And what is typically happening in the Sciano cycle is that one of the reaction is a bit slower than the other ones. The reaction producing oxygen 15 out of nitrogen 14 is the slowest. And because of that, there is an accumulation of nitrogen in the core. But this is typically happening in the core. If you, on the other hand, combine this with some equation for rotational mixing, so a diffuse equation for the chemicals that is given in this equation, you can then have some nitrogen produced in the center that is then diffused to the surface. And this can provide some nitrogen enrichment. And the diffusion coefficient appearing in this equation is typically rotation dependent, and that's why it's called rotational mixing. I will illustrate that on, again, some abundance profile plots. Just as before, this is the center, this is the surface, mass fraction and mass coordinate. So this is typically the abundance profile of a model at the zero enrichment sequence, where everything is just uniform. But then if we let time evolve, what will typically happen is that the Sciano cycle will kick in, hydrogen will be depleted in favor of helium, and we'll have some nitrogen accumulation in the center. And if we then let time evolve further, we'll have some even more nitrogen accumulation in the center. And if we also account for this diffusion, you can imagine it's just a bit like a heat equation. You have more quantity to the left, so it will then be slowly diffused to the external layers. So as time goes on, the nitrogen is increased at the surface. So based on these theoretical ideas, we understand that the enhancement is technically supposed to increase with time, and also to be more efficient with high initial rotational velocities, because this coefficient D depends on the rotational velocity, and it's 0 for non-rotating stars. And so this is exactly what you can see in this plot by Meder and Mene, where you can see the enrichment in nitrogen as a function of the initial equatorial velocity. And actually, these lines must be seen as evolutionary tracks. This is the 0 main sequence, and this is the end of the main sequence. And so what we see is that at higher initial velocities, we end up with higher nitrogen enhancement. Also, from the theoretical part, this enhancement is supposed to be more efficient at high initial masses. And this is what we see in this plot, again by Meder and Mene, where you can see the enhancement, but this time as a function of the mass, initial mass. And you can also see different lines corresponding to different epochs. And if we look at the end of main sequence line, we clearly see that at higher masses, the enhancement is more important. And everything is summed up in this plot by Brodt, 2011. We have the velocity dependence, the initial mass dependence, and the nitrogen enhancement given color-coded. Red corresponds to a lot of a more important nitrogen enhancement. And as you can see, at higher mass and higher rotational velocities, this is where you produce the most nitrogen. And so how does that compare to observations? There is this population synthesis study by Brodt et al. 2011, where additionally to the stellar tracks, they actually performed a population synthesis simulation to obtain a distribution of which is corresponding to kind of the expected distribution of stars in this Hunter diagram based on their tracks. And we see that we really recognize this correlation in a sense between the initial velocity and the enhancement that we can now understand on a theoretical point of view. The problem is that the observed distribution doesn't really match the simulated one, as you can see. Well, there is a region where we have stars following this correlation, but there is also some boxes, the box 1A and box 2, that we can't really explain with single models. The box 1A is composed of stars that are rotating pretty fast, but that are not really nitrogen enhanced. On the other hand, the box 2 are stars that are not rotating fast, but that show high nitrogen enhancement. So it's not really possible to explain this distribution just based on single star models. And most of the explanations for these populations involve binary interactions, essentially. Box 1A could be created by post-mass transfer systems, whereas the box 2 could be made of merging products, or also stars that have been braked by magnetic braking. A bit of metallicity dependence, also coming from the theory, from the models by Brodt. As you can see, with the same physics but different initial metallicities, the enhancement is more important at small metallicities. So here, this is the SMC metallicity and galactic metallicity, because this enhancement in nitrogen is really the difference between the initial value and the final one. So it's the size of this bar, and you can see that it's bigger at low metallicities. So theoretically, we expect the nitrogen enhancement to be more efficient at low metallicities. And there are some recent observations that are relatively consistent with these predictions. This is a work by Martins, 2024, where they performed observations of stars in the SMC, LMC, and Milky Way. So we have some scatter in these populations, but if we would just draw some very rough average, comparing the SMC and the Milky Way for the most extreme ones, we do see that the average enhancement in the SMC is higher than in the Milky Way. And let me now move on to the last part of the presentation, which is focused on end products. I will start with supernovae and the supernova classification that you are probably familiar with. I will not tackle the type 1a supernova because they are not the end products of massive stars. I will only focus on core collapse supernovae. There are mainly two branches, the type 1 and type 2 supernovae, depending on whether hydrogen is seen in the spectrum. And then there are some further subdivision. For example, the type 1 is subdivided into type 1b and type 1c, depending on whether helium is in the spectrum. And there are also some observed relative fractions of the different types of core collapse supernovae. This, for example, diagram is obtained by Smith 2011. And as you can see, there are much more type 2 observed supernovae than type 1b and 1c. And so on the theoretical part, how can we connect the observable properties of different types of supernovae to the nature of the progenitor? That's the question I want to tackle in this part. So if we remember, the type 1 or 2 depends on whether there are some hydrogen lines. And so on the stellar evolution point of view, if we again consider our mass fraction plot, if we would have some hydrogen in the surface, because the star still has some hydrogen envelope, well, then we would see some hydrogen in the lines during the explosion. So this is typically the profile that would provide a type 2 supernova. But then again, if we had some important mass loss during the evolution, it's possible that at the moment where the star explodes, it doesn't have any hydrogen in the surface anymore. It's a stripped star essentially. This again could be due to stellar winds or mass transfer. And in this case, at the profile, at the surface, what we have is helium and nitrogen. And so if we have some helium, then we would expect a type 1b supernova. And again, if the mass loss was even stronger, it could have removed the helium nitrogen layer. And in this case, we would have only carbon and oxygen at the surface. And in this case, we expect a type 1c supernova. So now we probably clearly see a connection between nature of the progenitor and the supernova type with the schematic description that I showed. Blue and red supergiant are expected to provide type 2 supernovae, and Wolf-Rayet stars, being WN or WCWO type of Wolf-Rayet, would provide type 1b, respectively type 1c supernovae. And I think this is all very nicely summarized in this plot by Meder and Mene 2012. Where they show the expected type of supernova depending on some initial parameters, mostly the initial metallicity and initial mass, because stellar winds are stronger at high mass and at high metallicities. This is where we would expect the most layers to be removed, and it's indeed where we see that we would have some type 1c supernovae, whereas less massive stars or less metallic stars that have less stellar winds are expected to provide type 2 supernovae. And then if we keep that in mind and combine it with the initial mass function that are obtained from observations, as you probably all know, the more massive stars are less frequent than less massive stars. And actually, this kind of gives some sort of theoretical explanations for the core collapse supernovae fraction that we observe, because we do observe some more type 2 supernovae than type 1, and type 1 are also the ones that are created by more massive stars. Finally, I would just want to mention other types of supernovae. These are more theoretical supernovae. They are the electron capture supernovae for stars between 8 and 10 solar mass. And for most massive stars, there's another type of expected supernovae, the pair instability supernovae, that is due to the pair production. This is a very theoretical type of supernovae. It's not been observed yet, but it's still something that we expect. And if this can have some consequence for the remnant distribution that we expect. This is a plot by Woosley 2002 that essentially shows as a function of the initial mass the type of remnant that we'll expect. Could be a neutron star, a black hole. And what appears in this distribution is what we call the pair instability mass gap. Typically, pair instability supernovae are expected to completely disrupt the star, leaving no remnant behind. And because of that, we don't expect to see any black holes formed in this mass interval. And finally, I didn't have time to mention all the types of different progenitors n supernovae type, but there is this map that was proposed by Galliam in 2007 that kind of relates different progenitors to types of supernovae. And we can, in particular, notice the red supergiant providing type 2 supernovae and Wolf-Rayet stars providing type 1b and type 1c supernovae. Let me now say just a few words about black holes and gravitational waves. So the end products of very massive binary systems are expected to be binary black holes. And since 2015, we actually observe gravitational waves that are interpreted as being merging binary black holes or neutron stars. Here you can see observed quantities of the first gravitational wave detection by the LIGO collaboration. These are the better constrained quantities of merging binary black holes. You have the chirp mass, the effective spin, etc. And so black holes and gravitational wave detections are important. They place strong constraints on the physics of binary systems because the merging timescale is actually very sensitive to the initial separation. It's depending on the initial separation to the power of 4. And if we just do some simple calculation, plugging some numbers, tensor the mass for the black hole and a merging time that is the age of the universe, we, in this case, obtain a separation, initial separation of only 0.1 AU. So that's a very strong constraint on binary systems evolution because the black holes need to be extremely close. There are different proposed formation channels. I will not enter too much into the details because this will probably be the subject of another seminar. Some of them involve isolated binary evolutions. Some of them involve dynamical encounters in dense environments. And another constraints that come from gravitational wave detections, if you combine a lot of them, is the black hole mass distribution. It's been obtained combining a lot of different observations of gravitational waves emission and doing some fits. And some things that are trying to appear from this distribution is a peak around 36 solar mass. Another point that is interesting are the fact that we observe some detections inside the mass gap. So if you remember about this permeability mass gap that I told about before, if we just consider single stars, we don't really expect to have a remnants, black holes remnants of these masses because of the permeability supernovae. So the fact that we do observe some black holes in this range either suggests that the limitations of this permeability mass gap are need to be re-estimated, or that these black holes are actually formed from hierarchical mergers. So they've already been merging with other black holes in the past. And finally, to make the connection with gravitational waves, another point that is important to mention are short gamma ray bursts. They are short 2 seconds bursts of gamma rays, and they're long thought to be associated to relativistic jet of merging double neutron stars. And so for the first time in 2017, it was actually confirmed. One merger event was observed in the gravitational wave emissions. So the 2 neutron stars did some gravitational waves that were observed, but there was also an X-ray and an optical counterpart. So there was a nice confirmation of this theoretical expectation. And here you can see the light curves in different wavelengths for this event. All right, I think it's now time to summarize this presentation. I would say that stellar codes are able to reproduce the main observed properties of massive stars, but there are still a lot of uncertainties and discrepancies between models and observations, whose origin are not always understood and often manifold. The samples we are dealing with at those high masses are always pretty restricted, but there are also large uncertainties both in the observations and in the stellar models. A point that I didn't tackle too much is that binarity and multiplicity is very common among massive stars, and it definitely complicates the picture. And so I think it's important to have all of these constraints in mind and to combine all of them if we want to improve the models. And here I just provide an additional list of constraints. It's definitely not exhaustive. Multiplicity in binary fractions, mass loss rates, variability, circumstellar material, magnetic field, asteroseismology, and apsidal motion in binary systems. And thank you for your attention, and I'm now open for questions.
Thank you very much for this fantastic talk and overview with a lot of information, a lot of information. So now we open for the discussion, question and answer part. So if anyone has a question, please raise your hand and then you get the opportunity to ask your questions. Don't be shy. Yes. Oh, two questions. I see Ilek. Please, you can ask your question.
Hi, thank you very much, Luca, for the great presentation. In the very first part of your talk, when you showed the surface and central abundances as a function of the computed of the time computing with the Geneva code, the drop in hydrogen occurs more or less at the same moment. Was it like a coincidence? Was it like in this specific system? Because I would have expected envelope depletion through winds to be relatively independent from core depletion due to nuclear reaction. If you come back, more back, that was
Okay.
that was before blue strikers.
So you're saying that essentially it's striking that
yeah.
the depletion is
of the black line. So
the
is
depletion
there
in the center?
is there anything about like envelope core mixing regarding rotational mixing or overshoot in this simulation?
So I've not done this simulation myself, so I cannot tell you precisely, but probably the thing is that here it's one fixed mass. Maybe we would have obtained some very different things at different masses. Maybe one thing that we could say is that here it's the end of the main sequence, and so the star will then transition to the more red part of the chart diagram, and so maybe at this point the stellar winds would change. So this is maybe something that could explain that the fact that then following this early, like a few moments later, the whole envelope is stripped. But I'm not exactly sure because I've not done this simulation myself.
Okay, thank you.
I think that they also do include some LBV winds at some point. And when they kick in, they're pretty dramatic and they can remove a lot of mass pretty fast.
Okay, cool. Thanks.
We have a question from David Concha, who has some problem with his microphone. So he asked to elaborate more about this discrepancy between evolutionary mass and dynamical, in which cases one is more accurate than the other one.
So it's the mass discrepancy, right?
The discrepancy between evolutionary mass and dynamical masses. So the mass that are derived from light curves. And in which
it's not
one is
that,
more. I don't think
so it's not that part.
I don't think it's talking about the spectroscopic mass, but would be better.
I'm not exactly sure which slide then.
Yeah, this was not mentioned in your talk. When he means really the dynamical mass, please confirm via email, via the chat, please. When you really mean the dynamical mass, okay? Sorry.
I was referring about the discrepancy problem. Sorry. So I think now it's talking about the discrepancy between spectroscopic mass and evolutionary mass.
So this part, right?
Exactly. In which case is
so
one is more accurate than the other one?
Okay. Well, it's definitely not my expertise, so I could not say, to be honest. We can have some, I think, important entities in both cases. Which one is better in which situation? I don't know, to be honest. Personally, as an evolutionary a person more familiar with evolution, I would say that I think this evolutionary mass is pretty simplistic. But I guess that also the other way to obtain a value for the mass can also be suffering from important uncertainties. So I couldn't tell which one is the best.
So maybe I can comment on this as well, and maybe other people just on this question, because I'm working on this problem since 30 or 40 years. So I can speak only about the spectroscopic mass. I mean, the evolutionary mass is, of course, also hampered by certain assumptions and simplifications, but the same is true also for the spectroscopic mass. So the first thing is that measuring the gravity is per se not so easy due to a lot of different things. So one thing is, for instance, that you need very precise spectra with almost no signal, with a very high signal to noise ratio, because very few deviations of 1 or 2% can change the gravity quite considerably. This is number one. And number two is that the derived gravity also depends, for instance, on certain assumptions about the turbulence in the photosphere. So whether you assume no turbulence, as many people do, or a reasonable number of turbulence will change the derived gravity quite considerably. And from the gravity, then you have to calculate the mass finally, which involves, as you have shown, either the luminosity or implicitly the radius, meaning the distance. Even only nowadays we can derive, thanks to Gaia, the distance a bit better. So the transition between gravity and mass is quite good. So a lot of people are working on this. It does not seem to be a problem of the different codes, because in this figure you have shown, there are the results of the two prominent spectroscopic codes, and you see that they behave quite similarly. So there is a problem in the spectroscopic mass as well as in the evolutionary one, and we hope that at some point these will meet, or this will tell the discrepancy will tell us where we really have to repair something.
I think Sergio also has a comment about the mass discrepancy, and yeah.
Yeah, so just to you have to unmute. Okay, now Joe was mentioning about the, I'm hearing myself, about the gravity and the spectroscopic mass, but also the evolutionary mass have some caveats. So for example, one of the things that we need to know very accurately, the luminosity, and this again has been only possible now for galactic stars thanks to Gaia, but also, for example, for the luminosity, we have to take into account the potential effect of how you obtain your extinction to the star and some other observational things. So this is also affecting in some way, plus the thing that depending if you obtain the evolutionary mass using the HR diagram or the Kiel diagram, it would be different. In addition, depending on the tracks and all the things that Luca had been mentioning, that the tracks are going to vary depending on the physics that you consider in your evolutionary models. And the last thing is that now we know that the percentage of binary interaction products that will be hidden in the single star population is very large. So apparently single stars that actually are the product of a binary interaction. And then the luminosity over ratio is going to be different. So if you compare the spectroscopic mass with the evolutionary mass using single tracks, this can be also affecting your conclusion. So probably all together is what is making this problem to be there for so long. So hopefully soon we'll have some solution for this.
Okay, thank you, Sergio. We also have a question from, or a comment maybe, from Gloria. So please, Gloria.
Gloria.
Yeah, thank you. Well, the original question actually mentioned dynamical masses. And this, as Joe pointed out, was not mentioned in the talk, primarily, I guess, because the talk is aimed at the basic single star scenarios. But a dynamical mass is the mass that you obtain when you're able to see the radial velocity curves of two stars. And so if they are eclipsing, it's pretty straightforward to obtain the actual mass. I mean, it's the only circumstance under which one can actually, quote unquote, measure the mass of a star. So in a binary system, you get a dynamical mass. And I do not remember right now whether the dynamical masses are, whether the spectroscopic masses are closer to the dynamical masses when this has been done for binaries. Of course, when you have a binary, you have complications that have to do with the interaction of the two stars. And I'm talking about main sequence binaries. I'm not even talking about anything that has evolved or gone through mass transfer, just simple, plain, ordinary, very close to the main sequence, zero-age main sequence binaries. So what you want to have is you want to have binaries that have a relatively large orbital separation so that your interaction effects are minimized. And so my question to everybody here is, to what extent could these very well characterized binaries whose masses are well determined, rotation velocities are relatively well determined, radii are well determined from the eclipses, to what extent can these be used to sort of constrain the surface, the microturbulence and the macroturbulence and all these additional effects that introduce uncertainties into the spectroscopic masses?
Anyone wants to? Yes, Sergio?
Yes, so it's great what you comment, Gloria, and obviously is the way to go in the future. And unfortunately, with the large surveys, we'll have more and more double line eclipsing binaries together with TESS and other photometric surveys that we have. But then one of the things that I've always found difficult is to derive the spectroscopic gravities, you need to disentangle the spectrum from the two stars. And while this is quite easy for the case of metal lines, for the very broad hydrogen lines is not so easy. Maybe there's some people here that can give a different opinion, but my impression is that always these methods for disentangling the spectra are producing things in the winds of the Balmer lines that then are affecting your gravities. So at least for the comparison with the spectroscopic masses, there will be some kind of difficulties. I don't know if anyone has any comment in this regard.
Apparently no one, or someone who is shy wants to. Then I guess we're gonna leave it as an open question until someone comes with an answer. I can see in the chat that we have another question from Hanno Stinshoff. Do you want to ask it directly, or should I ask it for you? Maybe I can start asking for you. Is asking about, could you talk a bit? Okay, the microphone is also not very good. So the question is, so we switch a bit, could you talk a bit more about why only nitrogen was enriched at the surface in the rotational mixing in your presentation? So that's for you, Luca.
Okay, I think this I can answer. So firstly, I've done it pretty simply. I've not shown all of the elements. I've only shown the cyano elements. But if you look closely, actually, the ONC were moving a bit during the animation. I'll show it a bit now again. So the thing is that you have nitrogen that is, created at the center, and on the other hand, oxygen and carbon are actually depleted. And so in this case, the diffusion goes in the other way because you don't have any ONC at the center. You will have diffusion that goes in the other way. So this actually decreases the surface oxygen and carbon. So if you look closely during the animation, ONC are depleted, and this is what we expect from mixing. You have the increase of nitrogen, but the depletion of oxygen and carbon. And I cannot really tell more about other elements.
Okay, the person has another question. What about the helium, which is also created in the process in the core?
Yeah, there will be also some sort of diffusion probably. I've not really schematically represented it here. Actually, if you look at hydrogen and helium, they stay completely constant in the animation. But I think that what these kind of models show is that you will also have some diffusion, and typically then even your hydrogen would be a bit decreased and your helium would increase a bit because of that. I will need to check that, but I think that's what we would observe.
I think this can be commented by Sergio, because one of his students, Carlos Martinez, he himself and I himself have just published a paper on this question. So Sergio, go on.
I was just writing in the chat, so this is multitasking. So if you can repeat me again the question, sorry, because I was doing on it.
Helium over nitrogen.
Okay. Yeah, one thing we've found, yeah, but this is very preliminary. Yeah, this is like also when you have mass transfer, your surface is going to be differently contaminated by these products. So yeah, the point is that I don't know exactly the question, so I don't know what to. We can talk about this later, because I was doing
Sergio, the question is if rotational.
Okay, then I can,
sorry.
Since Sergio was just not concentrated on the talk, I didn't see this. I can give you a short point on this. So basically, helium, of course, is produced inside the core, but because of reasons which have to do with mean molecular weight, it is diffused outwards later than CNO. So what you would expect theoretically is that at first you see a nitrogen enrichment where the helium is not more or less changing, and only when the nitrogen enrichment is already quite strong, then you begin also to see some helium enrichment. So this is what you would see from a single star evolution. However, as it turned out, and this is a new paper by Sergio and particularly his doctorand Carlos Martinez, there are a large number of objects where you see the opposite, namely a lot of helium and almost not very much nitrogen, let's say it in this way. And the idea in this case is, again, what you have already told us, namely that we have finally also to account for binaries, where you can then explain these kinds of very strange ratios. But as I said in the beginning, binaries will be the subject of one of our next series. So we have to begin with something. And so maybe we should, in this discussion, if you like, concentrate at first on single stars when there are more questions. Sorry, Sophie.
No worries. We have Gloria who wants to say something. So please go ahead.
Yeah, I am struck by the fact that binaries are being invoked when I am not clear. I personally am not clear as to how well we understand the transport processes inside the star. I mean, how we have this problem of overshooting, convective overshooting. That's one. But then you mentioned diffusion. There's also the shear instability of the stars rotating differentially. So there's a whole bunch of processes that can transport heavy elements from the core to the surface. But somehow these are being brushed underneath the rug, and we're assuming that we really do understand these transport processes, or am I just so old that I don't have any new information and I don't know what's going on anymore in the world?
Do we have Raphael Hirschi here? Because he is doing this, Gloria.
I don't think so.
No, Raphael, so that's sorry. So of course, this is an old hat. Currently, we are doing a lot of approximations, particularly regarding these diffusion processes, which are related to a lot of very different processes. One is the transport from the core through the so-called transition zone, which has to do with the overshooting. Then we have transport by convection in the core. Then we have rotation, we have the shear, we have the so-called meridional circulation. All this, by the way, who is interested will be presented in talk number 4, I think, of this series. And so this will be done in more detail. But in any case, all these, of course, are 2 or typically 3-dimensional processes. And so we are cooking down all the 3-dimensional processes to a 1-dimensional diffusive description, which of course works only after we have convinced ourselves that we are not doing something wrong. And there are certain people in the world, for instance, Raphael Hirschi, who was also a member of the Geneva group, who is now sitting somewhere in the UK, and he is doing three-dimensional calculations of short regions inside the star. There are other people who are doing this, and at some point, I hope that they can compare then finally their results with a simple diffusion approximation, and then we know, at least theoretically, how to calibrate these diffusion coefficients. Whether these calibrations then have something to do with reality, this will only the comparison with observations allow. Luca, do you? Yeah.
Yeah, I just wanted to interrupt you because I see that Corinne is
Yeah.
yeah, and maybe it's on that topic. So
yeah, of course.
Yes. Thank you for giving me the floor. Yes, what George just said is totally correct. We are having some troubles because of these processes. My point is that, so I'm more on the low mass star side, but what we have to face now is that the transport of chemicals is strongly related to the transport of angular momentum. And what we are facing now is that actually the processes that we have been including so far for quite some time are not sufficient enough to transport the angular momentum as constrained by the asteroseismic observations. So at least for the low mass side, we know that there are other processes than the one you mentioned, which are already quite complicated. And there are different aspects related to instabilities, magnetic instabilities, or also to internal gravity waves. I think that now the community is really everybody agrees on these aspects, that we need to move into that direction. And there is a lot of effort being devoted to that. But really the very important thing is the seismology, the asteroseismology that has, let's say, help the community face this reality that as long as you don't know how to reproduce the rotation inside the star, you can always kind of fine-tune parameters for the transport of chemicals, but it's still not what we want to do. Actually, it's we need to make some efforts into that direction. That's all what I wanted to say.
Yeah. Thank you. Luca, or maybe Miriam also, do you want to comment on that topic, or otherwise we can switch to another one?
I think all's been said, and having the experts both from the observational part and the theoretical part, there's little we can add. But I guess the solution to this is to get constraints with very good, accurate abundances on a very large number of stars. Until we have that, we will not be able to provide constraints to the theoretical models.
Yeah. Agreed. Then I suggest that we switch to another topic. So Sergio, please.
Yeah, so I have one question, because this is also in part educational for everybody, and I wanted to ask Luca a question, and then I'm also interested to know what is the opinion of other people. So Luca, you've been mentioning about this blue to red supergiant ratio and how this depends on metallicity. So maybe you can go to the corresponding slide. So then the question here is, what is for you that you're a student working in models? What is for you a blue supergiant? So when you make these ratios, what do you include? Because the red supergiant is more clear because it's everything that is there in this part, but the blue can consider many things in the middle. So what is for you a blue supergiant?
Well, actually, I had to precisely look for the definition when I started writing the slides, because for me it was also not so clear. But I think what I found is that what we call a blue supergiant depends on the luminosity, essentially, and on the color. But so it's more, I think, in terms of evolution, we always use these terms. Like when it's still in the blue, we call that a blue supergiant, and when it's moved to the red, we call that a red supergiant. I've not exactly myself been working on this thing, so I could not tell you exactly at which stage we can call it a supergiant or not, to be honest.
Because something, and then I would be interested to know if someone, especially students, wants to answer this. But I will suggest you to think about this from the theoretical point of view, since you are working on models. So, because at the end you are providing numbers, prediction in terms of numbers that you compare with the observations. So think if this blue supergiant is very diffuse and this problem is quite old. So what we now know about the blue supergiants is not the same as 40 years ago. So think about what you mean when you talk about these ratios from the theoretical point of view and see if there is a good match with what people say in terms of observations. Because maybe also the problem is there, is that we are not speaking the same language. So maybe in a few months or years, we can go back to this discussion and you will tell me. And if any student has some idea, suggestion there, I would be interested to hear.
If I may jump in very quickly, I think this very same question is the reason why Luca made this second or third slide about the different species, the different shapes that where we can find massive stars, the OB types, the blue supergiants, red supergiants, and so on, at least to, you know, to give us the framework to know what we are discussing about. And if you recall, he did define absolute magnitudes and temperatures for the
maybe Luca, you can go to the plot, because this is interesting. This is something interesting for educational purposes.
Yeah, so when I was in this slide myself, I actually suggested him that he should include also the OB supergiants in the category of blue supergiants. But you are right. Maybe we should transition from morphological classification into boxes of luminosities rather than absolute magnitudes and effective temperatures.
Yeah, because basically the point is that since you have been mentioning, Luca, that the location of the times is not so clear, depending on how you consider where is it in terms of temperature, your percentage of what you consider is a blue supergiant would be different. So
yeah,
that's the point. This is why we need to define where are the population in terms. In the past we needed the morphology, but now we have parameters for the stars. So we need to define boxes and compare things in the HR diagram with quantities, not just morphology. But it's not only you, it's something that is happening to the whole community. Or many people in the
and I guess
community.
the root of the problem is that this actually comes from the photometric studies, where you used to have the color magnitude diagram with the plume of blue stars and then the red stars, and then you just did a circle and counted stars. But now that we can create synthetic populations and we know effective temperatures and luminosities, we can compare exact boxes from both sides and overcome this. Yeah. Very good point.
Anyone else wants to comment on that point? No? Then we have Satyam Soni who wants to ask questions. So please, you can unmute yourself and ask the questions you wanted to ask.
Hello, everyone. It was very nice to be in the meeting. It was very good presentation. I wanted to ask from the slide number 9. Can you quickly switch to slide number 9? I see different layers in the star. Does this model consider the magnetic field or the effect of magnetic field in these regions?
I don't think it's definitely implemented. I mean, it's not like in these stability criterions, nothing is said about the magnetic field. But I'm wondering if it would really alter the criterion or not.
I asked this question just to confirm
mostly
that.
Yeah.
Please continue.
These gradients are mostly they're mostly depending on the internal structure, on different gradients of different quantities. Magnetic fields could alter maybe these gradients, but at least they're not definitely implemented in the description.
Yes, because I wanted to know whether this discretely can explain this. Definitely discretely cannot explain the solar activity that we see as CM, coronal mass ejection or coronal loops in sun, but can this, I wanted to confirm, can this discretely alone, this model can this explain the solar activity or the coronal loops?
No, I don't think so. There's nothing said about the magnetic fields in this description, at least.
Yes, so it definitely requires implementation of magnetic field in the model to explain such coronal loops and other things as well.
Yes, I guess.
Okay, there is a follow-up question, very quick question. In pulsating star, does there is a discrete layer or a region which separates from radiative to this adiabatic region? In the pulsating star, does the acceleration of the masses in those regions is it different from each other?
Different from what, sorry?
In any other star? Does the acceleration of the masses in both the regions are they?
Is that
I
me?
think I think he froze, right?
Yes, I think so.
Am I
Let's see if he
audible and visible?
yeah, can you re-ask your question, please? Because you were frozen and we lost you. Yes, I think we see you now. Yes, can you re-ask your question, please?
I was asking in pulsating stars and in some stars which lose, a shell in different stages of their lifetime, does to account for those, I was thinking, does these difference in the densities and in the mass, in the acceleration of the masses in pulsation, due to the pulsation, do they have different accelerations so that one layer leaves behind the another layer, and it accounts for the for a shell that outburst from the star?
So I'm not an expert on radial pulsation, so I can't answer every question. Sorry, I don't know if someone can answer.
Anyone
I don't know
expert on
whether
radial
this
pulsation who wants to answer? No one?
I don't know whether this question does mean anything or not, but it was just, curiosity of my mind.
Well, sorry, but we have no experts on radial pulsation that can answer your question. So,
okay. Maybe I'll connect via email to Sciarini.
Yeah, sure. Let's do that. Well, it's been an hour and a half that we have spent together, so I think our brain need to stop unless there is a very necessary question that pop up to someone's mind. So if you do agree with me, I suggest we thank the speaker again for this very nice talk and the questions and the answer to the question. And we also thank Miriam for the supervision of this talk. And yeah, let's say goodbye. But before we leave, I remind you that next week we have the second lecture that will be given by Debasi Dutta on massive star structure, and he's going to talk about a fundamental equation governing the structure of stars. So please join us like today. And yeah, thank you for your participation today, and we see you next week.